Okay, flip it over to the camera here, get it all set up for today. Okay, so optimization is kind of, it's like a really useful thing. I'll kind of write off to the side, because some people are saying, like, when do we ever use this? Optimization has applications in economics, business, medicine, engineering, and it's basically kind of like finding an optimal amount. They're finding optimization. So like sometimes they want to maximize profit, like in business, you'd want to maximize your profits. Sometimes I'm just thinking of something like minimize the amount of materials you use. You know, if you want to save money, if a company wants to save money, they want to do, make the most money using the least amount of supplies, lower their costs. So optimization, what it does is it finds the most or the least of something. Most or the least amount of something. Like if a company, I was thinking of just like Amazon, if they're shipping things, they want to fit the most they can in the box, or save on shipping costs, use the least amount of materials. So there's applications of this in the real world. So we're going to look at some different story problems today. In interest of time, there's 4 on these notes. I think we're just going to do 3 of them. I was thinking just Nick's number 3, the third example, just to interest of time. So we're going to look at example 1 here. Find 2 numbers whose sum is 30 and whose product is as large as possible. Product is as large as possible. So see, we're trying to maximize something. Find the maximum product. So when they're talking about 2 numbers, we need to use variables and label our numbers like x and y, that's probably, or a and b, whatever you want to use. So 2 numbers, I'll just use x and y. So is it okay if we say our 2 numbers are x and y? And the 2 numbers, the first sentence says 2 numbers, their sum is 30. So is it easy to think about just x plus y equals 30? Does that make sense? It's kind of easy to make an equation out of that first sentence. Find 2 numbers whose sum is 30. Okay, so we got that. And then it says their product, we want that to be as large as possible. And you know what product means? Multiplication, okay? So now they want us to multiply these numbers that we're dealing with and get a product as large as possible. So I'm just going to write P for product. Product would be just taking x times y. And we want that product to be as large as possible. P for product, see? So product, I'm just labeling that P. That product word P. Try to make P as large as possible. Maximize our profits. Okay, so this equation is, how do I want to say it? Or how did I label it the other day? Like our primary equation, this is the one we're most concerned about. This is the one we're trying to maximize, make this one as large as possible. And this is like a secondary equation that goes along with it, because it's like another relationship they gave us. So you want to get your main equation, like your primary equation, this one, we have so many variables. Do you think we could maybe use this equation? Could we get this product equation down into one variable instead of having x and a y in it? Do you think we could use this equation so that maybe we could substitute so we don't have x and y? Like, what if I took this problem over here and solved it for y? Subtract x. So I'd have y equals 30 minus x. Then, couldn't you take this and plug it in here for the y? since y equals 30 minus x. So now I have my product equation, this one I'm trying to maximize. It's the same as x times 30 minus x. And that's what you're going to want to do on this optimization. There's usually a couple equations you're working with, but you have to think, oh, this is the main equation that I'm worried about because that's the one we're trying to work on and find the large product as possible. So this, they would say, is like the primary equation, and you use the secondary equation to usually plug in to that one. Well, now I could distribute this, right? I could distribute this and have p equals 30x minus x squared. Now we just got done with these first derivative tests and second derivative tests. So remember, when you do the first derivative, you can find your critical numbers and figure out if they're maximums or minimums. So we're going to use that concept. We're going to use like our first derivative test to find our critical numbers and decide if they're maximums or minimums, because if we can find a maximum, then we'll find the large answer we want, a maximum. So we're just going to take the first derivative of this, p prime, first derivative. What would we get for the first derivative? Yeah, 30 minus 2x. Okay, so if we take our first derivative and set it equal to 0 and solve that, let's see what we get. So subtract 30, divide by negative 2, x equals 15. So remember, that's a critical number. So we want to test that number and see if it's a max or a min. So 15 is our critical number. So we want to test numbers from negative infinity to 15. And 15 to infinity. And figure out where our graph's increasing or decreasing and see if this critical number 15, what it is. Is it a maximum or a minimum? Well, let's pick a number lower than 15. What's something easy that's lower than 15? 0. So what do you get if you plug a 0 back into this first derivative? So I'll write p prime of 0, like plug in 0 back into the first derivative. What do we get? Yeah, you get 30. Good job. So that means the graph's increasing there, like going up there. And then let's pick another number. What's a number between 15 and infinity? Anything you want. 16, sure. So let's do p prime of 16. Let's plug 16 into there. So it'd be 30 minus 2 times 16. So 30 minus 32. That'd be negative 2, wouldn't it? So that's negative, so that's decreasing. See if I can squeeze that in there. So if the graph's going up over here and going down over here, what's 15? It's a max. So I believe that would be the right answer, because they said find what would make the product as large as possible. If x was 15, that'd make the product as large as possible. So we're getting x is 15. That gives you a maximum, like to maximize your profit. Well, now remember, our answer, our problem had x and y in it. So if x is 15, we got to figure out what y equals. You could go back to one of the original equations. If x is 15, what does y equal? 15. Yeah, 15 plus 15 would equal 30. Yeah, so y would be 15. So yeah, the 15 would give you a maximum product. Because if you times 15 and 15, also you get a pretty big number. Maximizes the product. So the first derivative test helps you figure out if these are max or mins, and you can test them. Okay, so hopefully that's, pretty, not too bad. I know it's like two equations you got to work with though. Yeah, the story problems can be a little tricky to figure out. All right, so then we'll look at number 2 here. This one's a totally different question. This one has a graph here. What point on the graph, y equals square root of x, would be closest to 5, 0? Like, is it a point here? Is it here? Like, what point would be close to that? Like where? Like, you got to get exact. Like, some point up here, what point on this graph, on this curve, would be the closest to 5, 0? So you got to think, like, what kind of equation are we talking about? Or what are we talking about? Closeness. What are we talking about? Yeah, like you're going to minimize, like a minimum what? There you go, distance. Yes, it's a minimum distance. Good job. So you're going to have to use the distance formula. Because we're trying to minimize the distance. So you're going to have to use the distance formula. So if you're trying to find a point on the graph up here, and you don't know what the numbers are, couldn't we say we're trying to find an x and a y point? Some point up here on this graph that's closest to 5, 0. And this was the point 5, 0. Yep, you're trying to find the shortest distance between some point up here and 5, 0. So we want to do the distance formula, and we can use these x, y, and 5, 0. So distance formula equals, remember it was like x2 minus x1 squared plus y2 minus y1 squared? Remember your distance formula? It's in a square root. So I'm going to write x minus 5 squared plus y minus 0 squared. So this is the important formula. We're trying to minimize our distance. So I would say this is the main formula we want to use. This is the primary equation, our book calls it, like our main equation we want to deal with. And we had a secondary equation that said y equals square root of x. This that they gave you they gave you the graph equation. But this is the one we're working with the most because we want to figure out how we're going to get the minimum distance. But we can use this one secondary and use it to plug into the other one. The reason you use it is because you want to get it so you don't have so many variables. We have x's and y's. So what if I went over here and then see that y right there? What if I replaced it with x squared? Wouldn't that be not too bad to do, easy? And then the problem here will just have x's, and it'll be easier to work with. So hopefully that makes sense. You're always trying to get down so you don't have so many variables. So we got to kind of work this out, make it a little better. So we have x plus 5 squared, and then this is going to be square root of x. And if you take square root of x minus 0, what do you get? So I'll just write square root of x squared. See, like that. It's the quantity squared still. Still have the squared on it. And I would go ahead and square these things inside. Work this out, make it so we can work with it easier. So we have to take this x minus 5 and square it. Like x minus 5 times another x minus 5. Do FOIL. Work that out. And because I don't have a ton of room here, I'm just going to, you guys know how to take x minus 5 times x minus 5? What would you get?
X squared minus 10x plus 12.
There you go. Yep. And then what's the square root of x squared? Yeah, an x. Good job. And then we could combine. There's that minus 10x, and then there's this x. So we could put that together. So that'd be minus 9x plus 25. Yeah, it's trying to get that all inside kind of cleaned up. And I'm going to write that that's a square root's the same as 1/2 power, too. I like kind of writing it like that, too, when I get it all set. Yeah, so you have to plug in and you have to work on getting this all kind of cleaned up before you take your derivative. See, I didn't even take my derivative yet. You have to plug this in, get it all kind of cleaned up. Now I'm going to take my derivative of this and set it equal to 0 to see if I can find a max or a min. So now I'm going to take the derivative. So it's going to be 1/2, and then this to the negative half power. X squared minus 9x plus 25 to the negative half power. And then remember, it's a chain rule, so you have to bring the 1/2 forward, this whole thing to the negative half power because I've subtracted 1, then times the derivative of this inside stuff. What's the derivative of the inside stuff?
2x minus 9.
2x minus 9. So I would write this as, I would put it now back as a fraction. D prime equals 2x minus 9 over 2 square root of x squared minus 9x plus 25. See the 1/2, so there's a 2 on the bottom from the 1/2. This goes to the denominator. That's square root of all that in the denominator. Okay, so finally we're getting there. We took the first derivative, then you set that equal to 0. When would this derivative equal 0? Yeah, when that numerator equals to 0. If you take 2x minus 9 equals 0 and solve that, you'll get the answer. You get, what, 9/2. X equals 9 over 2, which is, what, 4.5? Okay, now, if you look at that graph, too, if we look back up, I think we're getting, see, it's looking like it's going to make sense. They're saying about 4.5, when x is 4.5, you're at the minimum distance. So then, just to check it to be sure, you're supposed to do that first derivative test, check points on either side of the 4.5, you know? And then keep in mind that your domain on this one, your x, we're not going to plug in, we're not going to go to negative infinity this time because the graph started at 0. This graph, the domain of this graph goes from like 0 to infinity. So we're just going to go from like 0 to 4.5 and then 4.5 to infinity for our little intervals. So 0 to 4.5 and 4.5 to infinity. Kind of squeeze that in there. I know these take a lot of room, so so pick a number lower than 4.5. Yeah, something easy. I might even pick 1 because 1's kind of an easy number to plug into things. And then pick a number higher than 4.5, like 5 or 6 or whatever you want to pick. 5's good. And just to check it, it's looking like that's probably is the answer, but they do tell you to check. So plug 1 into this first derivative equation and try to think of the sign you're going to get. Think of your signs. So if I plug 1 in there, let's see, 2 times 1 is 2. 2 minus 9 is negative 7. So the top I'm getting like negative 7. What do I get for the denominator if I plug a 1 in? Let's see, 1 minus 9 plus 25. I get like a square root of 17, so that's coming out positive. I'm getting like 2 times square root of 17. So I'm getting a negative 7 over like 2 square root of 17. So I'm getting a negative. So my graph's decreasing there, like going down. I'm getting a negative, so my graph's decreasing. And then if you plug in a 5, 2 times 5 is 10. 10 minus 9 is 1. And if I plug in a 5 down here, hopefully it's still like, it's probably positive is what I'm thinking. But let's see, 5 squared is 25. Minus 9 times 5 plus 25, yes, 5. 2 square root of 5, that's positive. So this graph's increasing over here. So is that point, that 4.5, is that the minimum? Yeah, it's like going down then up, so that'd be a min. Yeah, so does it make sense? That seems right. 4.5 seems like the right answer. And what point on the graph is closest? We really should then plug in 4.5 into here, and so you could get your y value, or it was 9/2. You know, so I know I'm running out of room. X was 9/2 or 4.5, and if you took like the square root of 9/2, you would get 3 over square root of 2, 3 square root of 2 over 2. You can put your xy point then. So if you plug in the 4.5 or the 9/2 into that square root, then you can get your y value. 9/2 and 3 over square root of 2, or 3 square root of 2 over 2. Yep, trying to squeeze it in there. They take a little bit. Okay, finally, last one. They're getting harder as we go. This one's the trickiest one. 2 towers. So you do have to think about what formula you're using too. Like, they didn't tell you to use the distance formula. You had to think, like, what is this? They're looking for distance. Yeah, so you have to think, what formula is this? So same on number 4. They might not tell you exactly, come out and say you're using this formula. You have to think about it. All right, so this one has 2 towers. I might use my space over here to draw my picture. 2 towers are 30 feet apart. One tower is 12 feet high, and the other tower is 28 feet high. So one's taller than the other, 28 feet. It said they're 30 feet apart. 2 towers are 30 feet apart. All right, one is 12 feet high, the other's 28 feet high. There is a stake in the ground between the 2 towers. And the top of each tower has a wire tied to it. They're trying, kind of like they're holding the stakes up with a wire. You know, it's like staked to the ground, so we'll just put like a stake right here. So there's like maybe a wire here coming down from the top of the towers to the stake in the ground. Yep, the top of each tower has a wire tied to it that connects to a stake on the ground. Where should the stake be placed to use the least amount of wire? So they want to use the least amount of wire. Least amount, like a minimum amount, right, of wire. Okay, well, the wire goes here, the wire goes here, the wire is going to be going here. We need to try to like label this, how we want to, like how do we want to label these. All right, well, also we knew this was 30 feet apart. If you don't know, okay, we know the whole thing's 30, but if we don't know like how far it is where the stake is, what could we put here? If you don't know a value, what do you think you could put? Yeah, let's put a variable like x. And then what about this distance over here? Well, you know, it has something to do with this 30. What do you think, Mason? Yeah, 30 minus x. Like it's a difference. Like if this was 10, then if you did 30 minus 10, you'd get this one's 20. Yeah, so you do use the 30, but it's like a relationship. Yeah, so label one of them x, the other one's 30 minus x. All right, now we got to figure out like how we want to label where the wire goes. They want to use the least amount of wire. Well, this is wire right here. Like the wire would be going here, and there'd be wire here. So wire, let's just put W for wire. We're trying to figure out the least amount of wire. So we need some variables to label these sides too. You can actually use whatever variables you want. You're going to use some wire here and some wire there. So the book has this one Y and this one Z. It really doesn't matter. I've seen it put like, you know how hypotenuse, sometimes they put C, so I've seen C1 and C2. It doesn't really matter. You can label it how you want. But yeah, you have wire here plus some wire over here. So see, you have to kind of think, how do you set these things up? And we want to use the least amount of wire. So this is the main equation we're concerned with. We're trying to minimize the amount of wire we're using. But you can see we have these triangles down here. All right, so what do you think we could do with triangles? And we have some values on here. Somebody said it. Yeah, we could use the Pythagorean theorem since we have triangle relationships. Yeah. So we have like, we could do Pythagorean theorem with this triangle, like x squared plus 12 squared, 12 squared equals y squared. We could do a Pythagorean theorem equation there. And then this other one also, we could do a Pythagorean theorem equation with this one too. We could do either side, it doesn't matter. 28 squared plus 30 minus x squared equals z squared. So this one's a lot because you have a lot of letters. We have x's, y's, and z's. There's a lot of letters going on here. So this first equation right here, it has x and y in it. The other equation over here has x and z in it. Oh, it's a lot. I think I could solve this one for y pretty easily. You know, like y would equal the square, if I took the square root of both sides, y equals square root of x squared plus 12 squared. Does that make sense? Like to get rid of the y squared, take the square root. And then same on this one, I think I could just get z equals the square root of 28 squared plus 30 minus x squared. So then, these were these secondary equations, and I need to use them to help me to solve this main equation up here. So what do you think I should do now? Yeah, like if this is y, plug that in for the y. This is z, plug that in. Because then we'll be down to just x's in the equation. It'll be a lot easier. See, it's hard, isn't it? This is a lot. So you're going to have to plug this in back up here. So w equals this square root x squared plus 12 squared plus the z, which was this other big square root. Okay, we could actually take 12 squared, right? So we'd have x squared plus 144. Okay, let's see what 28 squared is. 28 squared is 784. And so you'd have to keep, these take a while to do. So you have to work this out. Let's see, that'd be 900 minus 60x plus x squared. Okay, what's 784 plus 900? 1684? Yeah. So, all right, so we got this kind of all figured out. We got it all set up. The other thing to think about is, again, like the last question I was telling you about, how the graph didn't go over to 0, over like negative numbers. You should think about in this one too, if you're using wire, are you going to be using a negative amount of wire? Yeah, so you're going to be using some wire, but yeah, we're not going to go and be using like x as negative numbers. So we'll think about that at the end when we evaluate it. So now you're supposed to take the derivative of these and then solve. So you can see it just takes, like the hardest part's getting it all set up, but it's the same as the other ones. Now we'll take the derivative of this, set it equal to 0, and find that maximum or minimum value. So in the interest of time though, I mean, I probably would just say like, see, then you'll take the first derivative, equal it to 0, and then solve. So you'll be able to, you know, there'll be questions like that. The hardest part's getting them set up, I think. You know, the beginning, all this like, okay, how do I think about this? So I want to give you time to start working on it. I can tell you the final answer for this one. This was x equals 9. But yeah, you could see if you could get it. We could kind of revisit it next class and see how you did, you know, how you're setting these up. And yeah, so I want to give you time to start these things. So the problems are on the computer. Now, and again, I don't want to give you a whole bunch of these. I might edit it down and make it less, because I know they take a while to do. So I posted them on there. How about just they take plenty of time, so how about just 8 problems? I think the first 8 on there, because they do take a while. So first 8 problems on the assignment, which I think is just like the first 2 pages, because there's 4 on each page, I believe, something like that. Yeah, I think I'll cut it down to the first just 8, because they take plenty of time, just as it is.